Hey, I'm Helmet with Lord's Boards. Today we're taking a deep dive into the hardware design of my latest creation, the RoyalBlue54L Feather, a feather-compatible board featuring the Nordic NRF54L15. What differentiates the 54L Feather from other feather boards on the market is its onboard debugger, which allows you to debug your applications like a true embedded engineer would. Instead of getting trapped in the cycle of adding printfs to a critical section of code, causing delays because of that printf, seeing crashes after your printfs have gone through, and then trying to diagnose the error in that way, you're able to actually, with GDB or another debugger, check the execution of your code and not have to guess. It takes a lot of the mental load that you would have to include in your head, actually get it out of your head and put onto your real hardware in the real world. The debugger is cool, of course, but the NRF54L15 onboard is cool as well. As compared to the NRF52 series, it is ahead by leaps and bounds. It's an ARM Cortex M33 as compared to the M4 of the NRF52 series. There's a peripheral RISC-V coprocessor on board. So any of those RISC-V fanatics, I know you're out there, you've got another toy to play with. Expanded memory as compared to the NRF52 series, so a meg and a half of non-volatile memory and 256K of RAM, and significantly better power consumption. If you compare the same situation on the L15 and then take it back to, let's say, the 52832, the classic of the 52 series, you'll see it reduces that current consumption by almost half. Without further ado, let's get into the hardware design of the 54L Feather. The RoyalBlue54L Feather was designed entirely in KiCad. I started on a pre-release version of KiCad 9, one of the nightly builds. Now we're on KiCad 9. One of the people from the KiCad project actually reached out to me and incorporated the RoyalBlue54L in the demo repository for KiCad. So in one of the future releases here, when you click this open demo project, the 54L Feather source will be sitting right here. It's licensed under the CERN Open Hardware license, so if you want to check it out, it will also be on GitHub, link in the description. Let's start by working through the schematic here. There are four major components, as I've divided it, of the 54L Feather. There's the debugger, which is an NRF52833. It's a debugger for one, so it has the typical connections you would expect out of a JTAG debugger and works with PyOCD or OpenOCD. It's also a USB to UART bridge because the L15 does not have a USB peripheral. You have to have some way of getting logs out of the device. The NPM 1300 Smart PMIC sits beside the NRF54L15 and does the typical PMIC things you would expect. So it has a couple of buck regulators, a couple of LDOs that can also function as load switches. But then it does things that you wouldn't find normally in a single part. So there's a battery fuel gauge, there's an LED driver, there are some system management features you would typically have to have an external IC for, but it's all wrapped up into that 1300. The connectors are the standard feather connectors, so 10th inch spaced headers with the proper pinout. There's a Stemma QT/Quick connector, JST-PH for the battery that matches the same pinout that Adafruit and SparkFun use for their batteries that the L15 has itself, and a BM15C module from Fanstel, and then some external I/O and LED, a couple of buttons, and some external flash. I think it makes the most sense to start with the NRF52833 acting as the debugger. It's sort of the gateway to the rest of the 54L Feather. The NRF52833 is a perfect fit for this because it has USB, has UART peripherals, and it doesn't require an external regulator to operate from bus voltage. So there is VBus coming in from your USB-C connector, negotiated the current CC1 and CC2, which gets fed to the 1300. There's an internal LDO that outputs voltage on the VDD pin. Then anywhere you see NRF52_VDD in this sheet, which is why it's this sort of net label, so it doesn't creep out of this sheet, you are seeing the 3.3 volts by default that comes out at the 833. This part here is a level shifter that sits between the NRF52833 and the L15. This OE, or output enable pin, sits here and only turns on if the NRF52833 is on, which 833 can only be on if USB is supplying voltage to the 833. This means that if this output enable pin is off, you don't get any leakage through the pins of the 52833 when it's off. So it's totally isolated from the L15. The other benefit is if you choose to operate the NPM 1300 at some other voltage instead of the default 3.3, let's say you run the L15 at 1.8 volts off of the NPM 1300, you can still communicate with the 833 without breaking anything. Next, we'll cover the NPM 1300. Here you have the battery input, and then right above VDD, which is the system power from Vout2. We use Vout2 because you can use one of these strapping resistors to set it to 3.3 volts at boot. Also included a jumper here that you can cut and then connect to something like a power profiler kit to actually characterize what the power your L15 is using actually is. The NPM 1300 is managed over I2C, so these pins sit here. I've used one of the GPIO on the NPM 1300 to act as an interrupt to alert the L15 if anything's going on, if it needs to come and read from the 1300. One of the pins is acting as an enable pin. So I've broken that out on one of the pins of the feather so that you can turn the whole system on or off with the 1300. You just have to configure that at boot with the L15. An RGB LED sits here and uses the 3 LED drivers available on the 1300. And secretly hidden here within the 1300 is a battery fuel gauge. So it's measuring the current coming out of the battery, the current going into the battery voltage to give you a really good estimate of state of charge with low power. It's actually a lower power method than the typical Coulomb counter you would find as an external IC. Talking briefly about the connectors, these are those 10th inch spaced headers. So analog section, SPI section, UART, some digital pins, I2C. The enable pin is there as you would expect. What I've added is a ship hold pin. So instead of adding another button, because I was tight on space for the ship hold feature of the 1300, you can access it here. JST-PH connector here for the battery, as I said, in the same pinout as the Adafruit Feather or Thing Plus boards, and a Stemma QT port. And now for the star of the show, the BM15C module from Vanstel, which incorporates the L15 in the QFN package. All of the required components you need to operate the L15, including the 32 megahertz oscillator, capacitors, inductors. The only thing externally required is this 4.7 microfarad capacitor for decoupling. And then I've included what is kind of optional, but is a power savings with this 32 kilohertz oscillator here. This is the NFC connector with its tuning capacitors. These are just the default values I found from the development kit. These are subject to change. There's an indicator LED that's connected directly to the L15 in case for some reason you can't or don't want to communicate with the NPM 1300 to drive those LEDs. A button that also is broken out to the pin header, and a reset button. This is an external quad SPI flash. Right now, the L15 does not have support for quad SPI. There is no hardware support for quad SPI, but in the future, there may be some development to enable that RISC-V coprocessor to talk to this over quad SPI. But today, you can use those write protect or hold pins in addition to regular SPI with this 2 megabyte external flash. That's the schematic covered, so I'll cover the hardware layout of the L15 Feather. This is the nRF52833 connected over USB to this USB-C port, protection IC, NFC port, Stemma QT or Quick connector, the battery connector, pin headers, as you would expect. This is the extra ship pin, the LED, external crystal oscillator, 2 megabytes of flash, and the BM15C module. In general, I would follow the layout guidelines provided by Nordic on their website to a T. In this case, the nRF52833 isn't actually communicating over Bluetooth, so I played it a little bit fast and loose as compared to what you might see in the datasheet, but I followed good best practices by keeping the decoupling capacitors close to the package, keeping vias to ground, in fact, in the pad, since I'm using via and pad on this 8-layer board. So overall, fine for this purpose. If you were doing a design of the nRF52833 and needed Bluetooth, I would follow that reference design very closely. The NPM 1300, since it's dealing with relatively higher currents and switching power supplies and stuff that's closer to magic, I was careful to closely follow the reference design here. So I would encourage you to do the same. And those are all available on Nordic's website. Thankfully, with the BM15C, all of the RF magic and antenna tuning is already handled for me. So I just kind of slapped this on the board, added the decoupling capacitor, and the external crystal oscillator was ready to go. Additionally, in this iteration, you'll see I've added castellated edges, changed it to the correct color, which it should have been blue to begin with, and then added some test points. So these 4 test points here are available to talk directly to the L15 if for some reason the 833 is not working. Then I've added some connections to the USB here so I can test the 833 and some of the critical voltage rails. So that is the RoyalBlue 54L Feather in review. If you'd like to learn more about this little board, please check out the Crowd Supply page at the link in the description or on screen now. Please like the video if you liked it, leave any comments or questions in the box below, and share with anybody you think might be interested. Thanks.